Okay, so today we're going to cover electrical concepts, and so we're going to go through a little bit of this, then I'm going to put you into breakout rooms, and today we're going to do random breakout rooms. So you're going to be in a room with maybe some of the people that you regularly work with, but you're going to also meet new people. Don't be afraid to ask questions or speak up or unmute yourself, because we want you asking as many questions as possible. It is 3 problems, and you will have to turn them in. So you're either going to have to take a picture of your work or use like Cam Scanner or notes on your phone to turn it into a PDF to upload it back into Blackboard by next Thursday's class. So I'll give you a full week to finish up the 3 problems, show your work, and get it turned in. Okay, so for electrical concepts, some of the things that we expect you to know are to really identify a voltage quantity when it is expressed in base SI units, describe that relationship between electrical charge and electrical current, define voltage and current, and describe Ohm's law, which I will go over, and then some of these other things as well. So if you're an electrical engineer or a biomedical engineer or a mechanical engineer, you're going to need to know at least some electrical concepts. It's always good, depending on what background or engineering degree you're trying to get, that you at least know the basics of how a basic electrical circuit works and how to calculate accordingly. And so when we're talking about electrical power, we're kind of referring back to our mechanical power. So we've covered power. And so power, remember, is work divided by time, or energy divided by time. And so that work can be broken down into a force times a distance. That power, when you break that down further, is really just a force times a velocity. And so electrical power, when we relate those two, your power for electrical power is equal to electric work divided by time, where that electric work can be broken down into a voltage times a charge. That voltage times a charge divided by time gives you voltage times your current, or P equals V times I is our equation there. And so getting power for an electrical device is really just your stored potential energy or electrons trying to repel throughout your circuit. So again, we bring up power for electric power is that voltage times your current. So we have our voltage here with our current that moves from the positive to the negative through some form of resistance. And so this is where Ohm's law comes into play of V equals IR. And so your resistance is a measure of how hard it is to push those electrons through a device. And so in your textbook, you find this table, 8-14, which goes over most of the electrical concepts that you will need to know out of the basics. So what is a charge? A charge is represented in units of coulombs. And so it's equivalent, a coulomb is equal to an amp times a second. And so it is related through Coulomb's law. Our current is equal to our charge divided by time. And so that coulomb divided by seconds will get you to your amps. So if you rearrange that first equation, you get the second. Your voltage is a volt. That is usually how we represent our batteries, is in voltage. Our Ohm's law represents our resistance, or gets us to our resistance using our current, and so on. And so our electric power, again, can be represented as V times I, which is also equal to I squared times R, or V squared divided by R, depending on how you rearrange your equation for Ohm's law and substitute in. And so that is always measured again in watts, like our regular power. And then we have capacitance and inductance as well. And so just understanding what units those come in and how they relate through the different laws and equations for electrical concepts is important. And so what we're going to do now is, using that table, go onto Blackboard, and on Blackboard under in-class quizzes, you're going to find electrical concepts, problem solving session, and I am going to break you out into those random groups right now so that you can start working on those problems with help from a TA. Okay, so what I want to do is I want to kind of get into chapter 12 a little, which is not, we took this out of the curriculum, but I think it's really important for you if you are going to be an electrical engineer or are really interested in electrical concepts, looking at the linear relationships that occur with electrical devices and the power in that. And so a lot of this relates to Ohm's law, capacitors, and inductors, and being able to calculate the current and resistance within a simple circuit, and things like that, or the capacitance or inductance that it occurs within a simple circuit. So if you are going into electrical engineering, and we are going to actually do a little bit of this in lab 4 in terms of, I believe, resistance. And so you will kind of need to know these concepts. So I want to make sure that I cover them here. And so looking at Newton's second law, so when a force influences a change to a system parameter, the system opposes that change according to its internal resistance. So normally we're talking about a force, so we're talking about work. And so looking at that force, the amount of matter in the boulder is the internal resistance that opposes the acceleration of the boulder, which is your change. And so when we're talking about this with resistors versus a mass or a physical object, we're looking at that force equals mass times acceleration, whereas for an electrical resistor, we're talking about the voltage is equal to our current times our electrical resistance. And so we get Ohm's law out of that, V equals IR, here written RI, but more commonly written V equals IR, which will allow us to calculate one of these 3 quantities based on the other 2. And so given Ohm's law, so V equals IR, so V is your force pushing the electrons around the circuit. So that's our voltage of our battery that is in the circuit. I is the change in the system, so how many electrons are flowing, or the current, which we measure in amps or amperes. And then R is our internal resistance in the circuit, the resistance being measured in ohms. And so 1 ohm is equal to a volt per an amp. And so if we look at, we have 2 different types of simple circuits. We have a parallel circuit and then also a series circuit. So these calculate differently. This equation is on your conversion equation sheet. So being able to calculate the equivalent resistance of resistors in a simple circuit is very important when you get into electrical engineering, into the circuits 1 class and so on. And so a lot of different engineering majors will have to take at least a circuits 1 class so that you understand these concepts for mechanical motors or for other aspects. So in parallel, we're looking at the same voltage or force is applied throughout our whole circuit. And so when we calculate our equivalent resistance, here we have 2 resistors, resistor 1, which has current 1, and then resistor 2, which has current 2. So our current is split between our 2 resistors. When our resistors are in parallel, we provide less resistance in the circuit. And so our equivalent equation to calculate our equivalent resistance is 1 over R1 plus 1 over R2. And so the little inverse relationship going on here for our 2 resistors. Whereas in series, we have the same current flowing through both resistors because they are in series with each other. So we stack 2 resistors on top, which means we have different voltages through them depending on where they are in the circuit. So our resistors in series provide more resistance within our circuit. And so the way we calculate our equivalent resistance for series is we just add up our resistances of our 2 different resistors. So if we have this question, so what is the effective resistance of the following resistors when placed together in series? So if resistor number 1 is 30 ohms, resistor number 2 is 20 ohms, what is our equivalent resistance?
50.
So very quickly, we should be able to add that up and get 50 ohms as our equivalent resistance. Now what happens when we put them in parallel?
It will be 1/30 plus 1/20.
And then 1 over all of that. And so we end up with our equivalent resistance being approximately 12 ohms when they are in parallel versus when they're in series of 50 ohms. Then capacitors. So our capacitors kind of work the same as our resistors. So where Q is the charge stored in the capacitor. So this is kind of like our battery, which is our voltage in our system. Our capacitor now is measured in coulombs. Our V is the voltage, and then our C is the internal resistance provided by the capacitor in farads. And so a farad is a coulomb per volt. And so when we put them in parallel, our coulomb equivalent now looks like our resistors in series, where we add the two. So this is actually opposite of our resistors. So when we put them in series, we now use our 1 over the inverse of our two capacitors. And so when we do capacitors in parallel and series, it behaves similar to springs. So springs and capacitors are very similar. Resistors and inductors are very similar. So talking about inductors, we have V for voltage, and then our change occurs in the rate of change of current. So that's current per second, amps per second. And then L is our internal resistance by our inductor, which is measured in henries, where Henry is a volt second per amp. And again, this occurs very similar to our resistors. So our series and our parallel look just like our resistors and behave similar to resistors when we put them in parallel in series. Okay. And so if we were to look at, again, we had a graph where we're going to do some graphing and understand what everything means. So understanding that linear relationship. So if I have a graph here with a trend line where we have V equals 1.9T, and we know that our equation, so we're talking about our inductance, our I over C. Okay, so we can then go ahead and calculate what our constant units are. So we know that's going to be volts per second when we move our T over the other side of our equation. And then the physical meaning of our constant is I over C. So this should look similar to kind of what I covered on Tuesday, being able to interpret our trend line on our graph. And so we take our theoretical equation and our trend line equation, relating the two. So what is our constant? What does it mean? Our volts and our time match up. So we know that our 1.9 is equivalent to our theoretical equation of I divided by C, which will allow us to take that and calculate based on the value of our capacitor given a current of 50 milliamps. So I'm going to leave this here. I'm going to give you the rest of class time to work in your groups. Once you finish your assignment, you can get it submitted, take a picture of it and upload it, or work on it at another time. But I want to give you the rest of class time, which is about 20 minutes to finish up anything. Or in those breakout groups, ask questions about A7, wherever you may be stuck. Or you can stay in the main room and I can help answer questions as well. So I'm going to stop the recording. I will get this uploaded for you, and then you can